So hi everybody. So today the promise was to prove the localization theorem, and let me recall what are we trying to prove. So here is this theorem. Let me recall the framework. We have a torus T acting on M, and M is a compact connected oriented manifold. I'm not sure whether last time I stressed that it was oriented, but we'll see that actually it is an important point. Now we're choosing an element in the Lie algebra of the torus, and we assume that the one parameter subgroup of this element. So this is a one parameter subgroup of the torus. If you take a closure, you get the full torus. So this is an assumption. Now, a further assumption. They're saying that we have a differential form on M, which is T invariant. And we define an operator, which is the sum of the Durand differential and the contraction with the fundamental vector field of X. So this is an operator acting on omega M and actually preserving omega MT. So this is an odd linear operator. And we assume that alpha is in the kernel of that operator dx. Maybe just to recall, last time there was quite a lot of discussion whether alpha depends on x. Now, in this setup, there is only one x. So from that perspective, of course, in some way, alpha depends on x because it satisfies a differential equation with it's in the kernel of the operator dx, and the operator dx does depend on x. But a priori, at this point, we don't have a family of solutions for different x's. Of course, if we're getting examples from equivariant cocycles in the Cartan model, then we get the whole family. So then we have a solution of this equation for all x, which of course depends on x. Right. So now, furthermore, we have simplifying assumptions. By the way, in the next problem set, we'll have a problem where those assumptions to some extent will be relaxed. So we're not doing the general case, not because it's not accessible, but just because it would require more bookkeeping. So we assume that the fixed point set MT is a finite set. So in fact, it consists of fixed points, let's say P1, Pk. K is, in this case, the number of those fixed points. And we discussed last time that this also implies that the dimension of M is actually even. So we can denote it by 2n. Of course, in a general case, if MT is not a finite set, the dimension of M may be odd. All right, so much for assumptions. Now, the conclusion of this theorem is as follows. So we integrate alpha over M. So by the way, here we do need the assumption that M is oriented to integrate the top degree differential form. And the answer is 2 pi to the power n. This n is half of the dimension. And then the sum over fixed points in MT. And here we evaluate alpha at P, and we divide by some funny denominator. And so maybe some remarks which would explain notation. So first of all, so this form is usually of mixed degree. So we can decompose it into homogeneous components, something like this, where alpha k is in omega k of m t. And it is clear that what we are integrating here is alpha to n, right? So this is only the top degree, which contributes in the integral on the left. And here on the right, when you restrict your form evaluated at the point P, this is only the component alpha 0, which contributes, nothing else. So a priori, these are very, very different components of alpha, which contribute on the left-hand side and on the right-hand side. But of course, we have the equation dx alpha equals 0, and that's this equation which links in some way different components of different degrees, and that's the magic. That's how it works. So this is one observation. So then I should say, what are those W's, or recall what are those W's? So sorry. So those W, Pj, so these are elements of the weight lattice inside T star, and these are the weights of the T action on the tangent space at the point P. So in particular, this means that this is a sum over J of C WPJ. So these are the copies of C or copies of R2 with those weights. Now here, in fact, there is something a little bit wrong or a little bit strange with what I'm saying. So here is a test question. Do you see what's wrong? So so there is a little bit of a problem with those weights, right? Anybody sees a difficulty? So here there is a little bit of a problem.
Oh, you mean the denominator might be 0? So the weight?
No, that's okay. Of course, that's let's say that's surprising, that's interesting, that's strange. But no. There is just a more basic question: is the right hand? Have I actually defined the right hand side? Let me give you a hint. So now the left hand side is clearly well defined, right? There is this alpha, right?
So Anton, what is X in this situation? It's arbitrary.
Oh, no, wait. X, in the statement of the theorem, we fixed X to be once and for all
Okay.
So
I
this
get
is a fixed element. So this is some concrete X. In fact, I think it contains, and this X is generic in the sense that the one parameter subgroup, which it generates, after the closure, it gives you the full torus. So that's why I think it contains the answer to Muse's question. So in fact, denominators, they cannot be zero, to be honest. But still, is the right-hand side well-defined? So I don't think well, one would need to look at it and prove that denominators cannot be zero, but assume denominators are non-zero. So there is an easier question about the right-hand side being well-defined. Remember, like, of course,
You mean,
yeah, go ahead.
so the manifold is real.
Yes.
But I think you need to complexify the TPM and then decompose, or no? What are you doing?
No. But you know, this is just my notation. I can also say R2, right? R2 with the weight WJP. I don't need to complexify. I can, of course, identify, but here it's already like close to the answer. Maybe. Yeah.
And these weights are this lattice is real too, or
sure. Yeah. This is all real. Yes. Yeah. Here there is no difficulty. The difficulty is maybe recall at some point we had a very elementary discussion about classification of representations of the torus, and then those weights, they were defined modular the sign, right? So if you're doing real representations, then if you change the orientation of your R2, so then the weight actually changes sign. We don't know, it's W or minus W. So for this reason, when I say, so the WPJ are the weights, you can ask what weights, right? And but if you fix the orientation of each R2, then there will be a well-defined notion of the weight. Now, suppose I fixed orientations of all my R2s. So this is more or less equivalent to saying what is the Z variable. We were choosing a complex structure on each of those R2s. But this would induce the orientation of TPM, right? But TPM already has an orientation, which comes from the orientation of the manifold. And we require that the orientations, meaning that the choice of signs of weights, would be such that these two orientations of TPM induced by the orientation of M and induced by the orientations of each two-dimensional subrepresentation. So those two orientations would be the same, because this basically is controlling the sign, right? Changing the sign of W's on the right-hand side would, a priori, it may change the relative signs of terms, right? We have a sum of terms for each P, and there are signs. And so maybe I should say, so there are two orientations. So orientation of M induces, of course, orientation of TPM, and orientations of those R2s for J equal from 1 to N also induce an orientation of TPM. And we require those orientations to coincide. So note that in principle, you can still choose orientations of those R2s. For instance, if you change two of them, two W's will change sign. But of course, this means that the sign of the product doesn't change. So there is no contradiction. So W's, they're still not well-defined objects, but the product of those linear functions is a well-defined object. Right. Okay. So one more thing before we do the proof. So I need to show you one more technical gadget. But that's really the last one before we do the proof. So, and it goes under the name of a real blow up. So what is it about? So suppose that I consider an open neighborhood of 0 in Rn. And this neighborhood will be of the following form. I assume that I have some Euclidean metric, some standard Euclidean metric on Rn, and I want U to be union of the origin. And so it's going to be a ball of radius rho, an open ball of radius rho. Right, so it looks like this, right? You have the origin, and then you have an open interval from 0 to rho times the n-1 dimensional sphere, right? U is an open ball of radius rho. So then I construct the following gadget. U hat, which will be a product of the semi-open interval. So I will close it on one side times Sn-1. So there is a natural map . So there is a natural map from U hat to U, which is called the blow-down map. And let me give you an example, just probably it's sort of easier to illustrate it on an example that everybody knows very well. So if I take n equal to 2 and I take a point of U hat, which has coordinates r and theta. Right now, the sphere of dimension n-1 is just a circle, and I map it to a point of U, which is given by Cartesian coordinates. Right, so this is just the polar coordinates map that you learn in the first year or at school, whatever. So some elementary calculus map. Now, maybe just to show on the picture how it looks like. So suppose that this is our neighborhood. Sorry, it must be kind of disk, but my disk didn't work very well. And here in the middle is the origin. And now, so this is a picture. This is a kind of picture of U. Now, what is the picture of U hat? Right. So U hat, it looks like this. And then you can imagine that here, instead of a point in the middle, you have a small circle. So the blow-down map is actually a diffeomorphism everywhere outside the r equals 0 place. And then at r equals 0, you have the whole sphere, right? 0 times Sn minus 1, which is contracted into a point, into the origin, right? So, so that's how it looks like. Maybe one more thing. Of course, my U was not closed, but what I want to say that now U hat has a boundary, and this boundary contains this 0 times Sn minus 1, right? So that's this place. So now maybe when we see what this construction is about, here is a remark. So suppose that Rn that we were talking about, it carries a linear T action, right? And here inside is sitting our U, which is defined using, say, a T invariant metric, and here is sitting our point 0. So then it's easy to convince oneself that the T action leads to U hat, right? And moreover, so this T action and let's assume further, sorry. So let's assume linear action, this isolated fixed point at 0, right? So the origin is an isolated fixed point. Now, what happens? So now I have this U hat. So the T action lifts. So the blow down map is an equivariant map. And what is nice? Now on U hat, there are no fixed points. So that's that's the construction. So we are introducing this artificial boundary around a fixed point, an isolated fixed point, and now there is an action on a space with a boundary, but now there are no fixed points. So now the idea is as follows. We now go back to our compact space M, on which we have a T action, and the fixed point set is a finite set of fixed points. So there are those fixed points. And now we do a real blow up at each of those fixed points. So we built, so this construction that I described to you is a local construction. I can do it by creating a chart near each fixed point. I model it on a tangent, on a piece of a tangent space. We discussed that this must be possible. And there I do this real blow up, and then I glue back that chart to my manifold. So I built a real blow up manifold. So here, each of those fixed points is replaced by a small sphere, and it comes equipped with a blow-down map pi. So, right. So this is a blow up at points of MT. So there is a blow down map, and now this M hat has a boundary, and what this boundary is, right? So this is a union of those spheres, right? These are spheres of dimension 2n-1 because our manifold was of even dimension 2n, and here I can label them by points of the fixed point set. Right. So perhaps perhaps a couple of more remarks. We have a T action on M hat. We have a map pi, the blow down map to M. This is a T equivariant map, right? Here we have a vector field xm. Its zeros are exactly the fixed points, right? And here we have a vector field xm hat. It descends to the vector field xm under this blow down map. And this guy is never zero, right? That's because M hat T is empty, right? So at the moment, it's not so clear whether it's a good trade, but I'm making a trade of our space, which has fixed points, to a manifold which has a boundary but has no fixed points. Okay. So maybe the last remark. We have an operator dx acting on forms on M and on forms on M hat. So this is d plus iota xm, and this is d plus iota xm hat. And so they're intertwined by the pullback under the blow down map. So the vector fields, they go from M hat to M, and the forms go from M to M hat, right? So that's so this is true because any pullback intertwines the run differentials. That's just the standard wisdom. And now that's because the map is T equivariant. Then those fundamental vector fields, they are related by star, and then by upper star, kind of you can go through with a contraction through the pi upper star, and so, and it works fine. So okay, so now we are ready to look at the proof. Okay. So now proof. Proof of localization. It will consist of 2 steps. And step one is very easy. So we want to compute an integral over m of alpha. So what I do, I pull back alpha to m hat, but in m hat, roughly speaking, right, m hat is different from m on some negligible subset, right? So I replace those points by n-1 dimensional spheres, but those n-1 dimensional spheres, they're still of codimension 1 inside m hat, so they are negligible. So this means that if I instead integrate a pullback of alpha over m hat, I get just the same. So those boundaries, they will not contribute anything. So that's basically what you are routinely doing when you are integrating, when you are making a change of variables in your integrals from Cartesian to polar coordinates, right? That's exactly. And then the Fubini's theorem tells us that if we're just adding those boundaries, it doesn't matter. Okay, so that's some kind of Fubini. Okay, so now on m hat, there are no fixed points. And then recall that on m hat, there is a form lambda such that dx lambda is equal to 1. Right? There is no such a form on m because there are fixed points. But on m hat, there is such a strange differential form that this kind of differential dx, which squares to 0 on invariant forms. So this dx times something is simply 1. Okay. Now, well, pi star alpha. So alpha was a dx cocycle. Because of this intertwining property, pi star alpha is also a dx cocycle. So dx pi star alpha is 0. And therefore, I can write it as an integral over m hat. And here dx of lambda wedge pi star alpha. So now we had the Stokes, we discussed the Stokes formula for those dx cocycles. And so this is equal to the integral of the boundary of lambda wedge pi star alpha. So this is Stokes, which is more or less the ordinary Stokes. Okay, but now what are those boundaries, right? The boundaries are exactly the spheres which are replacing now the fixed points. And when you take a pullback of alpha to those spheres, right? So that's the same as taking a pullback of alpha to the points. So this means that only the 0 component will survive, right? So I'm doing it on m hat, but I know that alpha came from m. So I can first, maybe I should say the following. Yeah. So if I restrict pi star alpha to the boundary component corresponding to p, this is the same as to take pi star of alpha restricted to p, right? It should commute those pullbacks. And alpha restricted to p, it only knows about the zero form part, because all the other parts, they will be simply 0. So now I'm getting, which is already nice, a sum over the fixed points, because they label those boundary components. Here, which is also nice, I'm getting alpha at those points P. And now I'm getting integrals over S to n minus 1 P of lambda. So note that these guys are just some numbers, right? So these are, let's call them CP. And these are just some numbers, whatever they are. So integrals of those mysterious form lambda over those spheres. Now there are several schools, there are different proofs. Now we need to compute those CPs. And there are several proofs. So there are some explicit calculations we build. So this lambda is not unique. We build some kind of lambda and explicitly integrate it. And I want to show you a very beautiful proof due to Mein-Renken. Of computation of those CPs, which goes as follows. So this calculation will be somewhat tricky, but very, very beautiful. So note that right, if you go back to the statement, what are those CPs? Well, what's the answer that we expect to get? So these are those 2 pi to the power n divided by the product of pairings between W and X, right? So that's the answer that we expect to get, but of course, who knows? Maybe we don't get it. Let's see how it works. So, right. Let me draw again my manifold. And I've chosen here some particular point P, and around that point P, I consider a neighborhood U. So P is sitting in U. Of course, here there is a T action which fixes P. And remember, we know that it's isomorphic to some neighborhood of P, but now inside TPM, together with a linear action of T. So locally, we can think that the T action is a linear action with that unique fixed point, which is our P. Okay, very good. So as before, we know that TPM is isomorphic to the sum. Let me still denote them by C or by R2, as you like, right? So it's isomorphic to a direct sum of n copies of R2 or of C with the action given by the weight WPJ. Now, we can say that we introduce on each of those copies of our 2 polar coordinates and then the vector field xm, the fundamental vector field, is equal to, again, here I'm as usual confused about the signs. So WPJ x d over d phi j. So note that these guys are all non-zero, and this is because P is an isolated fixed point. So if at least one of them were 0, then we would have had just the whole R2 of fixed points, or intersection of R2 with this neighborhood. Okay, so that's for the linear action. We simply explicitly know how XM looks like. Now let me manufacture, and this is something that you have seen already in the exercises. Let me manufacture the following two forms. So I introduce chi a bump function on the positive real axis, which is equal to 1 near 0. Then it descends to 0, and then it's 0 starting from some value of rho. So this is chi of rho. So a bump function. And I built the following equivariant form. But now even it doesn't matter that it's equivariant or not. I'm just applying this dx. And it's easy to see that this is minus chi prime of rho j, d rho j, d phi j, right? That's the Durand differential, plus WP jx. So these are coefficients of the fundamental vector field times chi of rho j. So for those of you who looked at the exercises, the tricky thing is, so this guy is actually not smooth. So this is not a good differential form. However, the right-hand side is smooth. So that's essentially because d phi is not a good differential form near the place where rho j is 0. And on the right-hand side, you either have chi prime, which is 0 when rho j is 0, or you just have this function chi of rho j without d phi now. And these are both very nice objects. So the right-hand side is a very well-defined differential form of mixed degree, degree 2 plus degree 0. And it is easy to check. I leave it to you as an exercise to check. It is T invariant, and it is dx closed. In fact, if that non-smooth guy, if it were a smooth form here, then dx is clearly dx closed, and so that would have been obvious. Now you need to work a little bit to check it, but of course, kind of it's clear that if I apply dx to something and dx normally squares to 0, then it should work fine. Okay, very good. So I don't know why, but I constructed those forms. And now I am defining alpha to be a product j from 1 to n of alpha j. And I would like to think of it as an element of omega m t. Do I have a right to think like that? Well, yes, because you see those alpha j's, they are all compactly supported inside their two planes, right? Now I take a product of alpha j's, and the resulting form is compactly supported on this neighborhood V, right? But then V is isomorphic to U, which is sitting inside my manifold. So if I identify U and V, so I obtain some differential form, which is T invariant, and which is compactly supported on that neighborhood U. Okay, very good. And of course, dx alpha is equal to 0. This is because dx alpha j was equal to 0 for all j, right? So I actually get a form which verifies all the requirements of my theorem. But now step 1, right? Step 1 implies that integral over m of alpha is equal to sum over p in empty, right? Alpha of p times cp. But now the form alpha is compactly supported near one of the fixed points. So this means that it is just 0 near all the other fixed points. And so on the right-hand side, there is only one term. What is this only one term? Well, we should evaluate. Let me go to the next page. So what is this one term? So this one term is equal to that Cp. And now we need to evaluate our form at the fixed point. Well, the evaluation for each of alpha j's, this is just this guy. But the bump function is conveniently equal to 1, right? So this is just a product of those weights. So that's the value of my form. Right. Okay. That's very good. Now, what about the left-hand side? So the left-hand side is also very convenient, right? We just need to evaluate the integral over this guy over a two-plane, and then take a product of those integrals. But those integrals, they are all the same, right? So the integral over d phi gives you 2 pi, and then the integral over rho gives you chi of 1 minus chi of, say, infinity, which is just 1, right? And this is all to the power n. So that integral, we just know, we just designed it such that it integrates. So, and this is equal to 2 pi to the power n. And so the conclusion is that Cp is equal to 2 pi to the power n over the product. Right. So as I say, this is one possible way to compute it. There are other ways. And I think, I don't know whether you looked at the in this Bismuth-Witten derivation. That derivation goes a little bit differently from the Berlin-Verne derivation that I showed you, but the result is always the same, fortunately. So we get the localization formula. So which I remind you is this one, right? So we've now proved this localization formula. So now I want to spend the rest of the class talking about applications to the of the story to Hamiltonian G spaces, and in fact also I want to introduce the topic of the next lecture. So in the end, I will formulate a theorem that we will be discussing next time. So complications to Hamiltonian, let's say, T spaces. Right. Okay, so as usual, we have T acting on M. So we have a symplectic form. We have a moment map, right? And then we know that omega T equal to omega plus mu x satisfies the equation dt omega t equals 0. So this is an equivariant cocycle. And then in particular, this means that for all x in T, dx omega of x is 0. That we discussed. And also we discussed, and that's what we're going to use now, that dx of exponential omega x is 0, and exponential of omega x, this is the exponential of the moment map, and here we can take the sum over s from 0 to infinity omega to the ss factorial, just the finite sum which we obtained from the power series of the exponential function, right? Because for omega it will terminate. So why I decided to speak about this kernel of dx instead of equivariant homology? That's because formally speaking, this exponential of omega x is not such a good equivariant differential form, right? It's some kind of infinite power series. In omega, it would terminate, but the exponential of mu x does not terminate. And usually in the definition of equivariant homology, we work with polynomials. So this is not at all a polynomial. However, for us now, it doesn't matter. We proved this analytic. So this BV theorem is not quite an algebraic topology theorem, right? It's some kind of analysis theorem that we've just proved, but so it's somewhat less conceptual, but as a consequence, we can apply it for whatever we find in the kernel of dx, and exponential of omega x is in the kernel of dx. So what does it say? So now, of course, for x, such that blah, blah, blah. So this exponential of Sx closure gives t. So now we know that exponential of omega x over m is equal to, of course, by definition, integral of that exponential function omega to the power n over n factorial. So this is equal to the sum over p in mt. So I should probably write 2 pi to the n, right? And here exponential of mu of p paired with x, and divided by this product. So as we already briefly discussed, we can now think of it as an equality of rational functions, because the left, this is true, the formula doesn't work for all x, And that's exactly because for some x on the right hand side, you're going to have zeros in the denominator. But as an equality of rational functions, it works. And in particular, there are the following consequences that's very parallel to what we were doing already last time when we were looking at the consequences of the localization theorem. So first of all, we see that those sums over T milf P, sorry, milf Px to the power L over the products so this is equal to 0 for all L from 0 to n minus 1, right? So this is because the left-hand side is simply smooth in X. But those contributions that I write, that if I expand the exponential function here in the numerator, right, I'll get some homogeneous expressions with respect to X. And the homogeneity of those expressions here is just negative. So when X goes to 0, they would blow up. So clearly there are no such things, right, on the left-hand side. So they must be 0, right? So very interesting and surprising identities on the values of which relate the values of the moment map and the weights. So you cannot put those things independently. They kind of know about each other. And of course, if you put now L equal to n, right? So then we take 2 pi to the power n sum p in mt here mu over x to the power n, and here let me, sorry, mu of p x to the power n, here n factorial, right? Product g1 to n wjpx. So on the left-hand side, this will simply be an integral over m of omega to the power n over n factorial. And this is the symplectic volume of m. So when all of a sudden you put the nth power, right, then on the left-hand side, we get a symplectic volume. And on the right-hand side, we get some funny, interesting, incomprehensible expression, but which only depends on the values of the moment map at fixed points and on the weights, nothing else, right? So, so very, very interesting. But it's a very, very small piece of information that we can get from those integrals that we are discussing now. So let me introduce.
Do you mind just reminding us about X? Was X completely arbitrary?
Now X is completely arbitrary. So we have on the left-hand side, we have a rational function of X. A priori, of course, as a rational function, we see it has some kind of, each of the terms, it has poles. But now the sum of them, of those rational functions, it's supposed to be just a constant.
Yeah, I understand. I'm just to clarify. So X isn't completely arbitrary.
Yeah. So this is
in fact, it's independent of X as it happens.
So this is an equality. Of rational functions. A priori, if X is in this dense, open dense subset where the closure of the corresponding one parameter subgroup is the full torus, then the left-hand side is really a well-defined function, and it must be constant. But of course, it's a rational function. And if this rational function is a constant on an open dense subset, it's just a constant. That's more or less the definition, what it means for rational function to be a constant. Or it's more or less a definition of equality of rational functions, right? So this is an equality of rational functions of x. So in particular, all those poles, they should all cancel. Well, okay. So now let me introduce a definition. So of so-called Dürstmann-Heckman integrals. And these are actually the integrals that we have just computed, right? So this is an integral of the exponential with respect to the Liouville form. So here we introduced the context where x was an element of T, but sometimes people consider x as an element of a complexified Lie algebra. And of course, those equalities of rational functions, they are all still true. So if you want, you can consider integrals where x is purely imaginary or x is purely real, or where x is an arbitrary mixture. So all those formulas that we have written before, in particular, this formula here, equality of this and that, it is true for any x. Right, so that's the first remark. Now we can actually think about those integrals in a slightly different way. So let's draw a picture. So this is our manifold M, and this is the vector space C star, and the moment map maps M to something. We're going to probably briefly touch upon it next time, and maybe then in some extra lectures we can touch upon it. So there is the image. Actually, those images are very nice. They're convex polytopes, but for now it doesn't matter so much. So here is some kind of image of right. So what we can do, we can think of this Liouville form as a measure on the space M, right? It defines a measure, and if we think in terms of the measure theory, we can take a push forward of that measure to the space T star. So this push forward will define some kind of maybe not so nice, right? Omega to the n over n factorial, that was some kind of very nice smooth measure on M, but now it will be perhaps some kind of ugly, or who knows, measure on the space T star. So let me call it d nu M of Xi, and this is called the Dürstmann-Heckman measure on a manifold M. So this is a measure on T star. Of course, as M is compact, mu is a continuous map, so the image is compact, so it's some kind of compactly supported measure on T star. So then the first very simple observation is that our Dirichlet-Heckman integral, right, by definition, this was an integral of the exponential under the Liouville measure. So I can rewrite it as an integral of T star of the exponential, again, under this Dirichlet-Heckman measure, whatever it is. So this is very cheap. This is just a consequence of the definition. So let me end up with a theorem, and if we have time, maybe with an example, or we'll see. But first of all, let me state the following facts, which will be useful for us, and maybe we discuss them in more detail next time. So first of all, if psi in T star is a regular value of mu, so then the level set is connected. Of course, we always assume that M is connected. So that's one interesting fact, but we need it for the following. So so there is a unique, discrete or finite subgroup gamma psi in the torus such that maybe I write it this way, that gamma psi is equal to the intersection of all the stabilizers of all the points on that level set. So here, you know, we were usually thinking that the action of the torus on the level set is free, but now I want to, for a moment, relax that assumption, just to give you a somewhat more general statement. If we were thinking that the action was free, then you can forget all this stuff. So so then let me state a theorem, and we're going to discuss the proof of this theorem next time. So let's say sin T star a regular value of mu. So then there is a very nice formula of the Dirichlet-Heckman measure at that point. First of all, on the neighborhood of that point, the Dirichlet-Heckman measure is absolutely continuous with respect to the Lebesgue measure. I don't quite know whether you recall that notion from the measures theory, but this means that if you take the Lebesgue measure on T star, then there is a function which multiplies that Lebesgue measure and gives a Dirichlet-Heckman measure. So what is that function? So that function is, sorry, the volume of the torus. I'll tell you in a second how to compute it. Divided by the number of elements of that gamma psi times the volume of the reduced space. Right. So that's kind of very, very nice in some way, right? So this Dustern-Heckman measure, it just more or less up to some minor coefficients. It's just the Lebesgue measure times the volume of the reduced space. Now, one small remark. Right, so to compute the volume of T, you need to choose the Haar measure on T, and choosing the Haar measure on T, this is the same as to choosing a generator of the top exterior power of the Lie algebra, right? So you need to choose one element and you integrate the volume form defined by that element. And in a similar way, what is the Lebesgue measure, right? Because we don't know what are the, you can choose coordinates on T star in different way. So you need to choose an element, let's say W, in lambda top of T star. So now one should require that their natural pairing be 1. So in fact, you see that that's kind of not neat. The product of these two guys is an invariant notion. Each of them maybe not. You don't know. You can make different choices. But the product of them is something well defined, is independent of the choices. So this guy is also God-given, and this guy is also God-given by the reduction theorem. So that's the formula for the for the Dustern-Heckman measure. And I would like to end today's class with a very, very simple example. So that's our standard example, an S1 action on a 2-sphere of radius r. Recall that it looks like this, right? You have a 3 space, you have a symplectic sphere of radius r. We consider rotations around the z-axis. So there are 2 fixed points, the north pole and the south pole. And the Dustern-Heckman integral is given by the integral of exponential of z times x, because z is the moment map, and times the form dz d phi, right? That's the symplectic form, and it's also the Liouville form. And by the localization theorem, so this is equal to 2 pi. And here the contribution of the north pole ZR over +1, sorry, over XR times +1 times X plus exponential minus XR over -1 times X, right? So this is, so these are the weights at the north and south pole. And this is equal to that expression. So that's the Dustern-Heckman integral. On the other hand, the reduced space m psi is equal to a point if psi is between minus r and empty otherwise. Right? So the Distrimont-Heckman measure by the formula that we had before. So we have the volume of the torus, which is 2 pi, times this characteristic function of the segment minus r to r. There we have reduced spaces which are points. Their volume is equal to 1 because we need to take an integral of 1 over a point times d psi. Now the alternative expression for the Distrimont-Heckman integral is integral of x xi, or maybe z. Let's leave it at xi times g nu s2r xi, and this is equal, of course, to 2 pi integral minus r to r x xi d xi. And, well, as expected, this is equal to the same expression. Of course, this is a little bit like a very, very trivial example. I think in the exercises, you will find a slightly more challenging example, which goes in the same direction, but I just wanted to illustrate how it works in the very easy case. So next time we'll go back, we will dive back into symplectic story. We'll talk about this theorem, and we'll talk more about how those reduced spaces look like. We'll look at the other aspects of the Distrimont-Heckman theorem. Okay, look, thanks a lot. I don't know whether you have questions or comments. Was the proof convincing?
Could you please repeat the part when we had this exponential of omega and these relations of the for the points of moment? This part.
Okay. Sure. Okay. Like we start, we just observe, right, that the exponential of omega.
So here we had not omega with index x, but I mean.
In principle, yeah. Now we have omega, which is defined for all x, and for all values of x, dx exponential of omega x is 0. But now we observe that if x in that open dense subset where the closure of the one parameter subgroup of the torus, then our analytic or whatever Berlin-Wern theorem applies, right? So then I just take exponential of omega x and integrate. Of course, this in practice means that I integrate the exponential function with the measure given by the Liouville measure. So that's this line, right? Now the localization theorem tells me that, okay, it's just equal to that expression. So restriction of the exponential, now symplectic form is gone, because when you restrict the symplectic form to a point, it's just 0, right? So the only exponential which is left for you is exponential of the moment map paired with x, nothing else. So that's how I get the right-hand side. Now I just observe that if I take an expansion of those exponentials in the numerator into a power series, I get on the right-hand side terms which are homogeneous in x of some homogeneity which is either negative or 0 or positive. But on the left-hand side, right, I know for sure that there are only positive contributions, right? Because I can also, here in this exponential, I can expand into the very nicely convergent power series. And I know that this is just a Taylor series in X. So for sure, all the negative homogeneity parts, they must be simply zero, right? Because on the left-hand side, I don't have them. And that's my first statement. And then the next statement is that, well, in degree 0, on the left-hand side, I'm supposed to get the symplectic volume, right? So that's just an integral of 1. And then on the right-hand side, I get some kind of tricky expansion, or sorry, tricky expression, which a priori depends on X. But in fact, since it's equal to the symplectic volume, it shouldn't depend on X.
I see now. Thank you. I just did not understand this during the lecture. This equivariant, this decomposition in series in X. Okay.
Yeah. Right. Okay. So, other questions? Look, people, if not, thanks a lot for participation. So we see each other next week, and I'll talk about this Distrom and Heckman, and we'll do more symplectic stuff. Fisa, if as usual you have a couple of minutes for an update, that would be good if you could stay. But so thanks a lot.
Okay.
Okay. Да, слушайте, ну что, вы посмотрели эту бумажку, как там вообще, чего там из нее?
Ну, она длинная. Я не вглядывалась, мы так посмотрели. Ну,
Вам еще не прислали, да, ничего от нас?
нет.
Ну,
ничего.
значит, вот какое дело. Наши письма для вас готовы. Так что, но, значит, и мы пытаемся подогнать, но там нужно еще, чтобы вас зачислило, чтобы университет вас зачислил. Это чистая, по-моему, формальность, но они, то есть мы с этим работаем, и мы пытаемся их подгонять. Это может быть еще чуть-чуть возьмет времени, тем более, что эта неделя у нас каникулярная. То есть там, ну, формально говоря, может быть, эта администрация работает, но сколько из этих людей на месте? Я думаю, все, у кого есть дети, потому что это школьные каникулы, и это университетские тоже каникулы сейчас. Поэтому эти все люди, они, наверное, отсутствуют, по-честному говоря.
Не, ну ладно, мы что, подождем.
Да. Когда это все-таки все придет, то там, вот я говорю, нужно, мы вам пришлем, ну, во-первых, вот инструкции я вам уже прислал с этим консульством, а во-вторых, нужно будет бежать, записываться в общежитие. Там вам тоже мы будем помогать как-то, но, значит, понятное дело, это там, скажем так, там есть, собственно, университетское общежитие, оно подешевле, и ну, будет как-то набрасываться, но в случае чего это немножко подороже, какие-то частные общежития, но лучше, наверное, бежать университетское.
И это как только нас примут, мы можем.
Да, к сожалению, мне кажется, для этого вам нужна вот эта бумага из университета, которая вот, с которой мы работаем. Но, да.
А что нам нужно сделать, чтобы наброситься на это общежитие? Там, это тоже?
Мы вам пришлем инструкции.
Ну хорошо, вы сами пришли.
Да. Вам нужно будет, ну, куда-то там на их веб-сайте, я думаю, записаться в очередь, там что-то. Но для этого нужна, по-моему, вот эта бумага, вы должны туда записаться. Может быть, вам выдадут какой-то номер студенческий, я, честно говоря, не знаю. Мне сказали, что эту бумагу нам нужно дождаться.
Понятно, понятно.
Хорошо, ну отлично. Ладно, в общем, продолжаем ждать, но если вам, я даже не знал, прислали вам уже наши бумаги или нет, это факт, что они не имеют особого смысла, пока нету бумаги в оригинале.
Ну да, да. Будем ждать.
Хорошо, ладно. Давай.
Ага, до встречи, да. До свидания.